Good morning, dear students. Let us start the second module, that is block diagram representation and signal flow graph. In this chapter, mainly we will be understanding how a control system is represented, pictorially, and how a control system represented graphically. The block diagram is a pictorial representation of a control system, which will express a cause-effect relationship of a system. That means a system will take an input and system gives an output. So a simplest block diagram looks something like this. A simple block diagram, will be as simple as a block takes one input and gives one output. And inside this block, you can have the mathematical operation which we are supposed to perform on the input, or I can simply take the name of the block, or this block can represent a function, or this block can represent a process. So this is about a simplest block diagram representation of a control system. Whenever we want to perform a signal subtraction or signal addition, we will be having a block, which looks like a circle. We call it as a summing point. Okay. And in the summing point, it takes the input, and we will use an arrow here just to say that signal entering to the summer or signal leaves the summer. So just to express that, incoming and outgoing pattern, we will be having arrows here attached to the summer. So input arrow says that signal entering to the summer, output arrow says signal leaves the summer. So, the summer can take many inputs and gives one single output. So it is going to perform algebraic sum. So why do we mention here algebraic sum is, if you want to find a difference of two signal, you have to take a first signal with a plus sign, and the second signal, if we take it inside a summer with a negative sign, we can directly compute the difference of the two signal. So finally we can say that here we are computing algebraic sum of the signal. And here you can see that it can be represented in different ways. So here we have a summer. As I said, a summer is a block. Look, it is a block becoming a circle to represent a summer. And here you can see that the two inputs entering to the summer and one signal coming out of the summer. So the plus and plus of this input says that the output is the sum of these two signals, because you can see that both the inputs are having plus sign. That means here we are performing addition of the signal. Similarly, if you want to perform subtraction, the first signal will be having the plus sign with the plus sign entering to the summer, and the second signal we have, it is entering to the summer with a negative sign. And what is the output here? Output is the difference of the two signals. So similarly, you can handle three inputs here, or actually you can handle n input signal using this summer, which gives the output, the algebraic sum of the input signal. So this is what the three input signal summer representation. And in few literature, you will find that a circle with an X mark represent the summer. So conventionally, I'll be using this as a summer, because in few literature, this is what the summer representation, symbolic summer representation. Okay. So this is about a summer. And in some situation, we will find, that we may have to pass a same signal to different part of the block diagram or different part of the system. So how can we do that? A same signal has to branch to the different point. Okay. So here entire signal is going here as a copy, and again the same copy going here, and again the same copy going here. The signal strength is the same signal moving or going to three different points, and this junction point we call it as a takeoff point. We are taking a copy of the signal to some other point here, and again signal is going to some other point, same signal going to some other point. This is what we call it as a takeoff point. So here also, we have a takeoff point representation. So we have a signal X in this line. You are taking a copy of that X and you are moving to some other point of the block diagram. So this is what we call it as the takeoff point in a block diagram. Okay, so I have an example here. So we have a mathematical equation here. So what is this mathematical equation says? This mathematical equation says that we have totally two input variable x1 and x2, and we have one output variable x3. So now x3, the output variable, is sum of these these input variable in this particular fashion. That is a1, which is a constant, into the first variable x1, plus a2 into the that is a2, the second constant, with the input x2, and we have one the minus a constant 5. So how can we represent this in a block diagram fashion or pictorial representation of this mathematical equation? How to do it? Let's understand. So since we have here signal addition or signal operation which we are performing, so we will be using a summer, which is performing the arithmetic operation on the signal. Correct? We are performing arithmetic operation on the signal, so we will be using this summer, as we have discussed in the previous slide. So we have a summer representation, and how many input it takes? You can see here three different terms we have. So we have three inputs to the summer and one output, and what is that output is what the x3 we have. So now the first input what I am taking, the constant a1 into the variable x1 I am taking, and the second input what I am taking, the constant a2 into x2. And mind the sign here. The sign of the input is plus and plus, because here they are added. So we have a plus and plus here. So I am taking plus and plus here. And finally, the third term is having a minus sign here. So the third input, the constant phi, entering to the summer with a minus sign. So we have output x3, which says that it is a1 x1 plus a2 x2 minus 5. That is what the pictorial representation of a mathematical equation we have done it. So now further we can say that instead of taking constant into the variable directly, I can make the make this variable pass through a block, a very simple block which can give a gain a1, and here you will get a signal a1 into x1. We can extend this directly. Instead of taking the variable multiplied with a constant directly we have fed to the summer, we can have more elaboration done here. I can have a block here, so I can make a variable x1 passing through this block, gets a gain a1, and can enter to the summer. So that's what we call it as the more clear block diagram representation. So that's what we have done it here. I have taken a block a1 a2 separately for the line 1 and line 2 signal input. So this is what we call it as the block diagram representation of a given mathematical equation. Okay, so similarly I can extend this to n terms. A summer can take n number of inputs and gives one single output. That is what we call it as algebraic sum of all the n inputs which we will be feeding to the summer. You can see here x1 x2 like that, xn minus 1. So that many inputs I can just fed to these summer, and you can see that based on the sign here, we are going to perform the summation here. So we call that as an algebraic summation of signals happening inside the summer. Okay, so next we have an exercise for you student. So here we have two mathematical equation given. We have to represent this pictorially. In other words, block diagram representation of this mathematical equation we have to do it. So how can we do it? I'll take the first example here. Look into the example carefully. We have output variable x2 and we have only one input variable x1. Correct? Here also x1, here also x1 we have. So what I do is I'll take one x1 signal I'll be taking. If I take one x1 signal, and that x1 should pass through a differentiator, and then it has to pass through a block with a gain of a1. Okay, and again you have to take one more signal of x1, one more line you have to take from x1, and you have to make that x1 pass through a block which is performing an integration, and it has to pass through one more block which is having a gain of 1 by b, and whatever the output we are getting from this line and this line, I have to fed to a summer, and finally we'll be getting the output x2 which we are looking for. Okay, so similarly for the next example, what I have to do, there are three terms you can see, and here plus I have, here minus I have, so that means you need a summer. So you need a summer here, and you have to feed how many signal? I have to feed, two signal, two, actually x1 and x2 are the only two variable. So you have to take a line x1 and you have to take a line x2. Okay, so x2 is passing through a double derivative block. You should take a block. Inside the block you have to write d square by dt square. That is an operator, double derivative operator. Through that, you will get an x2 coming with a double differentiation. Then it has to be passed through a constant a1. Okay, and that signal you will be feeding to the final summer. Similarly, the second term what we have, which is having an x1 variable. So x1 you have to take it, pass through a single derivative block, and again pass through a constant 3, and again you will find that third input with a negative sign you have to feed it, and x1 you have to take it from the same x1 which we are feeding in the second line. So this is what we have to do it. This is how we will be writing the block diagram representation. Okay, so next is canonical form of a feedback control system. Canonical form says that a standard mathematical form of feedback system. So here also we have a standard representation of a block diagram, standard representation or canonical form of a control system. So standard control system block diagram representation looks something like this. This is a standard form, or we call it as a canonical form. So we'll be having a summer, we will be having a forward path, and we will be having a feedback path. So this block is a forward block gain, we call it as. This block, what we have, we call it as a feedback path gain, or feedback block, we call it as. Okay, and this is what we have summer. You can have minus here or a plus here based on the requirement, and this is the input and this is the error, and this is what the controlled output we will be getting here. And we are taking this controlled output passing through the feedback is what the B signal we have, that's the feedback signal entering to the summer, generating a new error value. Okay, so we'll just see what are these variable again here. G is a direct transfer function, we call it as, or a forward transfer function. You can call it as a forward path gain, forward path transfer function, or forward transfer function you can call it as. And H is a feedback transfer function, and G into H is a loop transfer function, open loop transfer function we call it as. C by R is a closed loop transfer function. C by R is a closed loop transfer function. We also call this as control ratio. Okay, and E by R ratio, if I take this error signal to input, if I take, we call it as an actuating signal, or you can take it as an error ratio. Error ratio is given by E by R is equal to 1 divided by 1 plus or minus G into H. Okay, plus or minus G into H. So if you are having minus or plus here, you will get plus or minus here. Okay, so B by R is a primary feedback ratio, that is a feedback signal to the input signal R. That ratio, if I compute, we call it as a primary feedback ratio, B by R, which is equal to G into H divided by 1 plus or minus G into H. Characteristic equation. The control ratio is the closed loop transfer function of the system, as we have seen. The control ratio is what the final transfer function of the system, that is C by S by R of S is equal to G of S divided by 1 plus or minus G of S into H of S. Okay, the denominator of this transfer function, okay, denominator of the transfer function is what the characteristic equation. Why do we call this as a characteristic equation? Because this gives us the poles of the system. Poles are the point which wherein which you will find that system gaining the system gains a very high value. That is what important. Whereas numerator will be having zeros. That means the roots of this numerator polynomial will be carrying zeros. That means the transfer function will be getting a value 0 at those points. So we don't consider that. The denominator polynomial is what the characteristic equation which gives the complete behavior of the control system. Okay, so that's why we call that as a characteristic equation. So 1 plus g of s into h of s is what we call it as characteristic equation of a transfer function. Okay, so we have here an example. So this is what the canonical representation of a feedback control system. Okay, block diagram representation, canonical block diagram representation of a feedback control system. So here you have a forward path, correct? Here you have a forward path. Here you have a feedback path. I will call this block as G of S. I'll call this block as an H of S. As we know, input entering here, and here we get an actually error signal, and this is what the output controlled output C we have. How to compute open loop transfer function? Open loop transfer function is feedback divided by error signal. Okay, feedback divided by error signal, which we have already seen in the previous slide, that it is G of S into H of S. What is feed forward transfer function? Feed forward transfer function is output divided by the error. Output divided by the error signal that we have here. E of S is equal to, which is equal to G of S. This is what the forward transfer function. What is control ratio? It is output by input. Okay, final control output divided by the input is what the control ratio, which is given by G of S is divided by 1 plus G of S into H of S. Again, we have seen that in the last slide, and you have to substitute G of S and H of S, and you have to simplify. So feedback ratio, again, it is B of S by R of S, the expression we have seen. Control ratio, that is E of S divided by R of S. Sorry, error ratio, E of S divided by R of S, which is equal to 1 divided by 1 plus G of S and H of S. Because I have minus here, so I have plus here. Closed loop transfer function, that is control ratio, we also call it as output divided by input, which is equal to G of S divided by 1 plus G of S into H of S. You can see here closed loop transfer function and also the control ratio equations are same. It is same actually. So characteristic equation is what the denominator of this characteristic, the closed loop transfer function. The denominator of the closed loop transfer function is 1 plus G of S into H of S is equal to 0. So, the closed loop poles and zeros, you can calculate for taking some value K, and you can get all these equations. You can compute very easily. It is a very simple procedure. We have formulas written here. You have to substitute the G of S and H of S in all the equation, and you have to get a value for K is equal to 10. And you have to finally give me what is the closed loop poles and zeros. How can we say that? You have to take a closed loop transfer function here, and you will get a numerator polynomial and denominator polynomial. You have to find roots of those numerator and denominator polynomial, and number of roots in the numerator gives me the number of zeros, and number of roots in the denominator gives me the number of poles. So you have to substitute K value as 10, and you have to calculate the zeros and poles. That's an homework. You please do it. So now every time you will not find a control system represented in a single block or with a very few blocks. It is actually a huge, or a complex or a big system. You will find so many blocks are interconnected. The functional cross connections you will find. There will be lots of feedback loops, and several, loops exist in a block diagram. So we have to have a systematic approach to simplify them. Okay, and we have to reduce that to a canonical form. That is a standard form of representing a control system, wherein which you will be having a very simple very clear forward path, and you will be having a very clear feedback path, so that we can analyze the system and computing a transfer function will be easy. Okay, so we have to try to bring the given complex block diagram into a simple canonical form. So for that, we have to use some techniques so that we can simplify or reduce the given block diagram. So first, I'll will see the different techniques which we have, so that we can use them to simplify the block diagram. First one is the cascading form. Cascade, that is, if you find a series connection like this, different blocks, if you find connected in series, we call it as cascading here. Cascading connection, this pattern is called. So that time you can just directly multiply the gain and you can have one single block. Okay, so this is what we call it as a cascading of block. Okay, cascading of block, this is one reduction technique we call it as. So next to each other, if you find a block like this, if there is no disturbance, this we call it as a standard cascade pattern. So you can remove these two blocks and you can have one single equivalent block, and the content of the block or functionality of the block is the product of these two block gains. Okay, so next is combining a parallel block. So next technique we can have it the parallel blocks simplification. And here you observe, here same signal through G1 entering to the summer, same signal through G2 block entering to the summer. So direction here, if you see, so it is in the same direction. So we call these two as parallel lines. So parallel lines originating from the same point, meeting at the same point, we call them as parallel lines. Those parallel lines we can simplify. How? You can directly add these two and you can have one single block. You can eliminate the summer and you can have one single block whose value will be the sum of these two blocks. So this is what we have, a second reduction technique, that is combination of blocks, combination of parallel blocks. Okay, so we have next reduction technique, that is I can move the summer ahead of a block or behind a block. I can do that. I can take this summer ahead of this block, or I can, if it is present here originally, I can take it back. Why do I do that? Sometimes it is essential or required, so as to so as to simplify the block diagram. So we have here the summer moved ahead of the block. You can see here summer, which was present left to the block G, now summer has come to the right of the G. Okay, so now if you are moving the summer to the right, what actually happening? We found that the output of the summer now initially will not be having G. Okay, will not be having G. Now we will be getting G, correct? So if I move that here, we'll be getting G. Okay, so now what I do is I am going to subtract the G here. So summer I am taking ahead of the G, and this G is now getting added up here and appears here at the output point. So now what I do is I'll take here a signal passing through G and I am entering. That means the unnecessarily G which is getting added up, I am going to cancel it. You can see the minus. I'm going to cancel it. So I have to have one block G here. This is an additional block I have because of shifting summer to the right of the block. I have an additional block here, so as to cancel this G signal which is getting added up, and you will find the signal which we have here same as the signal what we had here. Okay, whatever signal we had here, the same signal will be having here. Okay, next, moving a summer point ahead of a block. This is, you can call it as behind the block shifting, and I'll call this as moving a block ahead. Ahead, that ahead and convention is left to you. So if you are having a summer here, you can take that summer to the left of the block. You can take that summer to the left of the block. You can call this as ahead, or you can call this as an ahead. See, that is what the convention, you can have it. Okay, so usually I used to, take this as ahead and this as behind. Anyway, we will follow whatever convention we have it here. This summer is moving behind the block. This is behind the block. This is ahead. This is ahead, front ahead, and this is back, beyond, behind we call it as. So behind movement, and this is ahead movement we can call it as. So this is what we have, ahead movement of the summer. So we can take this summer now ahead of the block. So if I take a summer ahead of a block, okay, I want to take a summer ahead of a block, that is here. If I want to take the summer, then what I should do, the signal strength should not get altered. Okay, so the signal strength, whatever you are having here, should not get altered. So what I do is, so G is entering to the summer, correct? G is entering to the summer here. Output of the summer is G, correct? Output of the summer is G. So now summer had come here. Summer had come here. Okay, so now output of the summer, is passing through G, is coming out here, correct? Passing through G, coming out here. Okay, so that G we are trying to cancel here. Okay, that G we are trying to cancel here. So 1 by G if you take it, 1 by G if you take it, multiplied by G here happening, so it will get cancelled. So you will get whatever signal you were getting, you will get that. Okay, whatever you are getting, you will be getting that. Moving up, what we call pick off point or take off point ahead of a block. So if you want to move this take off point ahead of a block, what we can do? So if you want to move this take off point ahead, sorry, pick off point or take off point, whatever it is, ahead of this block, what we do is, here if you branch out, you will not get the effect of G. Whereas if you come here, you will get the effect of G. So while coming ahead, sorry, while coming beyond, behind the G block, I will be getting the effect of G. That I have to cancel it. So I have 1 by G block here, and I'll find now the signal same what we had here. Whatever signal we had here, I'll be getting the same. So this is what we call it as takeoff point movement in what we call takeoff point movement behind the block. This you call it as behind the block. This you call it as ahead of a block. So this is what we call it as a behind movement. So ahead movement also I can do it. So I have a takeoff point here. I can take this ahead of the block. So while taking ahead of the block, what will happen? If I branch here, I get the effect of G, correct? Effect of G available here. Whereas if I go here, the effect of G I'll be missing. So what I should do? If I'm coming ahead of the block, this G I will be missing. That G I have to have it here by having a separate block G here. So this is what we call it as moving a takeoff point ahead of a block. Okay. So next is eliminating a feedback loop. So this is one technique. So you can see that this is already a standard canonical form. This is a standard canonical form. You can reduce this to one single block, and you can see this G, a forward path gain divided by 1 minus or plus, based on the plus or minus what we have here. We have minus or plus G into H. That means what? If you have plus here, you get minus here. If you get minus here, you will get plus here. That's what the meaning. So similarly, if you are having H unity feedback, if you have, that is H value, if it is 1, you will find that this block becomes now G divided by 1 minus or plus G. Very simple. This is elimination of feedback loop technique, we call it as. Next we have neighboring summer swapping technique. You can swap the summer which are next to each other. We can swap. So how we can do it? So it is very simple. We have signal A entering here, okay, and to this summer we have signal B entering, correct? So signal A entering here, signal B entering, say for example, what I can do is I can make B enters here and I can make A enters here. It is the same. So here, say for example, some input, I'll take it as say 1. So it is 1 minus A we have, correct? 1 minus A will be having, okay? So while performing addition at this stage or addition at the second stage, it is the same. So I can interchange or I can swap the signal here, which I am feeding to the summer. If two summers are connected in cascade, something like this, then you can swap the input signal. From first summer, the input you can take and give it to second summer, or you can take second input signal to the first one. You can do that. Okay, so we have an example here, that is the reduction of a block diagram to a canonical form. Okay, so we are reducing the given block diagram into canonical form. So how can we do it? As we have discussed so many reduction technique, we'll apply one by one and we'll try to reduce the given block diagram. First one is cascade rule, which we have learned. That is, try to identify where the blocks are in series connection. You have to identify and you have to simplify them. So I have done that here. G1, G4, or the two blocks, they are in cascade. So rule number 1, cascade rule, we can apply and we can simplify. Okay, that is first technique. And second, you can see here there is a parallel path G3. Through block G3 we have one path and we have another path through G2 meeting the summer, correct? So this is a parallel path we have that we can simplify. Okay, we have here simplified block diagram of this parallel path, which we have already discussed in the previous slide. So we can do that simplification. So that simplification is applied to the block diagram already. You can see that these two has been combined into one block, and this two block along with the summer has been simplified to simply G2 plus G3 here. Next, how to proceed with the further simplification. So you have here one canonical form pattern we have, that is one feedback path here. We have, it is not a feedback path. See, this is plus, right? So we have here the forward what we call positive feedback path we have. Okay, so we have to simplify. Okay, so we have to simplify this positive feedback path according to the formula what we have learned, rule number 7. Yeah, positive feedback we have, so we'll be getting negative sign here, and we have learned how to simplify this according to the formula. We have done it here. So this is what the equivalent block we have. So that replacement of simplified block is done, and these two found to be in cascade, we have to simplify, and we will be having one single block here and one feedback path. We call it as a standard canonical form that you can simplify. Okay, using again rule number 7, you can simplify that to get one single block. Similarly, we have a next example. We have to calculate open loop transfer function. We have to calculate feed forward transfer function, a control ratio, a feedback ratio, an error ratio, closed loop transfer function, characteristic equation, and closed loop poles and zeros if k is equal to 10. So we have to repeat all the procedures here, and once we reduce the given block diagram to a standard canonical form, then we will write equations for all these parameters, and we'll substitute k is equal to 10, and we'll calculate finally the transfer function poles and zeros, and that's the end of the part 8. Okay, so let us do this in the next class. I would like to stop at this stage. Thank you.